Okay, good afternoon, everyone. We're starting right away. Okay, today we'll be looking at inequality, means and inequality. So we have a warm-up problem here, which would introduce us to the very basic inequality theorem, if you like, that exists. Okay, we have this problem. So it's given that A, B, C, D are real numbers, and A minus 1 all squared plus B minus 2 all squared plus C minus 4 all squared plus D plus 3 all squared is equal to 0. Find A plus B plus C plus D. Okay, so the idea required to solve this is a very simple one. It's actually regarded as the most basic inequality idea we have, and that is every perfect square is greater than or equal to 0. Okay, that's just the idea. We need to solve this problem. Now, if you want to think of perfect squares, you realize that as far as we are dealing with real numbers, there's no perfect square that is a negative number. All right, 0 squared is 0, 1 squared is 4, negative 1 all squared is 1. So perfect squares are greater than or equal to 0. So clearly, we see that each term on the left-hand side, all right, it's a perfect square. Why? It's the square of another term, all right? We have established that A, B, C, D. The question says they are real numbers, so we know we are dealing with real numbers. If we're dealing with complex numbers, it's a different scenario. All right, it's a different scenario. So we clearly see that A minus 1 all squared it's a perfect square. Same with B minus 2 all squared, C minus 4 all squared, D plus 3 all squared. So each of these, so what we have on the left hand side is a sum of perfect squares. All right, and we know the smallest value for a perfect square is 0. Now on the right hand side we have 0, and this is an equality, means that the value of the left hand side is the same as the value of the right hand side. So if the right hand side has a value of 0, the left hand side must equally have a value of 0. And we know that each term on the left hand side is a perfect square. So this only works, this equality only holds if each of the perfect square is 0. Because if any of the perfect square is greater than 0, the sum will give us a value greater than 0. So for us to have the left-hand side give us a value of 0, it means each each of this perfect square has a 0 value. And that's the explanation I gave here. So that means that A minus 1 must be 0, B minus 2 must be 0, C minus 4 must be 0, D plus 3 must be 0. That's the only way we'll have 0 squared plus 0 squared plus 0 squared plus 0 squared giving us 0. All right, so if A minus 1 is equal to 0, it means that A is equal to 1. All right, same with B minus 2 equal to 0 means B is equal to 2. C minus 4 equal to 0 means C is equal to 4. D plus 3 equal to 0 means D equal to negative 3. You just make A, B, C, D subject of the formula in each equation. So the question says find A plus B plus C plus D, and it's simple. So what's A plus B plus C plus D? It's 1 plus 2 plus 4 plus negative 3. All right, so that's 1 plus 2 plus 4 minus 3, which gives us 4. So this is our warm-up problem, and it's basically emphasizing that the square of a real number is at least 0. That's what the warm-up problem is emphasizing. And this is like the most basic inequality idea we have to work with. That whenever you're dealing with real numbers, its square is always at least 0. Okay, so that is the idea we're going to build upon, particularly in our next class, because we're going to still be dealing with inequalities in our next class. Inequalities is one area that we get to see a lot of Math Olympiad problems. This class is more like a foundation class. We're laying foundation as to the ideas, the basic ideas that runs through inequality. So in subsequent classes, you're going to see this idea used more powerfully. So the objective of today's class, you're already aware of it. I shared it with you, various WhatsApp platforms, is that you should be able to compute quadratic mean, arithmetic mean, geometric mean, and harmonic mean of a given set of numbers. Okay, that's basically the first part of today's class. The second part is that you should be able to prove the QM-AM inequality. That's the quadratic mean, arithmetic mean inequality, the arithmetic mean, geometric mean inequality, and geometry mean, harmonic mean inequality for two values. All right. So we're not proving the general case. All right, we're just proving for two values. All right, that's A and B. All right. When I believe you're strong enough, we can now consider the general case where we have x1, x2 up to xn proving the general case. But for today's class, we'll just prove these inequality theorems for two values. All right, so let's discuss what means. Means are averages. As we already know that we're almost, yeah, all of us should be familiar with the word mean. All right, means are averages. A mean is a representative value of a given set of observations. All right, it means, so this representative value always lie between the smallest and largest observation. Thus, means are also called known as measures of central tendency. Yeah, I believe everyone here is familiar with mean, although some of you may have certain misconceptions about mean. For instance, some of you, your understanding of mean is more like arithmetic mean. Okay, some of you, what you know as mean is actually arithmetic mean, which is not correct, which is not correct. Okay, so that is the understanding you may have about mean. So mean is actually as measures of central tendency, the averages. All right, what we mean by means are averages, they are measures of central tendency, and we have more than one type of mean. We have various types of mean, which I'll explain. I saw a question. Please, I'm going to go through it. When I'm done with this slide, if you still don't understand, you can ask your question again. So there are various types of means. Is when you're taught mean, it's not just it doesn't mean arithmetic mean. Arithmetic mean is just one type of mean. It's actually the most popular, okay, the most well-known mean. Many people feel that that is the only mean, which is not true, as we're going to see in this slide. So we have some types of mean. Quadratic mean. Please note that quadratic mean is also known as the root mean square. Certain texts you may see root mean square, some you may see quadratic mean. They mean the same thing. We have arithmetic mean, we have geometric mean, and we have harmonic mean. Now, what is quadratic mean? Quadratic mean is the square root of the mean of the squares of the given observations. Yeah, this is math. I believe that seeing the formula will be more helpful. The next slide, we're going to see the formulae for each of these mean, but it's needful I give a definition, which is simply what I've written, the square root of the mean of the, okay, I should have said of the arithmetic mean is the square root of the arithmetic mean, and not just mean, of the squares of the given observations. While arithmetic mean of the given set of observation is their sum divided by the number of observations. Okay, geometric mean, actually arithmetic mean, you're quite familiar with what arithmetic mean is. Everyone here obviously should be very familiar with it. Now, geometric mean of a given set of n observation is the nth root of their product. That is, you multiply the observation and you take the nth root of it. That is, if there are 5 of them, the fifth root of it. Harmonic mean is the reciprocal of the arithmetic mean of the reciprocal of the given observations. Now, this may be a bit confusing, but formulas have a way of making things look clearer. Okay, so where we are, so given a set of n observations, x1, x2, x3, ellipsis xn, ellipsis xn, okay, so this is simply saying we have n observations. This ellipsis means we have, there are more terms that are not captured, all right? More terms, this is the first term, the second term, the third term, we have fourth term, fifth term, it continues onto a certain nth term, all right? So that's basically what this is saying. So how do we find the quadratic mean? I had defined it in the previous slide. Right now, I'm going to show you how it's done, the mathematical form. So this is simply the square root. So quadratic mean, for us to find quadratic mean of a set of observation, we simply take the square root of, we square each of the observations, add them up, and divide by the number of them. All right. So we have x1, x2, x3, up to xn. So we take the square of each, we add them up, divide by how many they are. All right, there are n of them, so we divide by n. Now we now take this, we now find the square root of it. Okay, this is how you go about finding quadratic mean, which is also known as the root mean squared. All right, which is also known as the root mean squared. Now, arithmetic mean already, you know arithmetic mean already. It is very simple. You just take the sum, divide some of the elements or some of the observation, divided by the number of them. Okay, some of the observation divided by how many they are. All right, some observation divided by number of observations. Okay, that's how you find the arithmetic mean of a given set of data. Now, geometric mean, it's as simple as arithmetic mean. You multiply what you're given and you take the nth root of them. So we have n observations. Okay, so we have x1 times x2 times x3 times ellipsis times xn, and we're taking the nth root of it. All right, so harmonic mean is equal to the number of observations divided by the sum of the reciprocals of the observations. Okay, we have x1, x2, x3, ellipsis, xn. So we take the n of them. So n divided by 1 over x1 plus 1 over x2, 1 over x3 plus ellipsis plus 1 over xn. So these are the formulae. Let's see some illustrations so that we understand better them. So we have find the quadratic mean, arithmetic mean, geometric mean, harmonic mean of 5, 5. So we have 4 fives here. I want to find the various means I've mentioned so far. So the quadratic mean, we know how do we go about it? See it here. You take the square of each observation, divide it by the number of observation, then take the square root of it. And that's exactly what we did here. 5 squared plus 5 squared plus 5 squared plus 5 squared. There are 4 of them, so we divide by 4, and we now take the square root. So 5 squared is 25. So this is 25, 25, 25, 25. There are 4 of them, so if you add it, you have 100. 100 divided by 4, that gives us 25. Square root of 25 is 5. Okay? Let's pay attention. So arithmetic mean, of course, we said in the previous slide, you sum them up, you divide by the number of observations we have, or values or elements we are given. So we're given 4, so we sum them up. They are 1, 2, 3, 4. So we have 5 plus 5 plus 5 plus 5 divided by 4. This gives us 20 divided by 4, and we have 5. Okay, we have 5. Please feel free to ask your questions. If you send me a chat and I don't see it, you could turn on your audio, um, and speak to me. Okay. Yes, we are establishing what these things are, and we're going to use it in a while. I said to this class we are laying foundation. These are first inequality class. So we are laying a foundation. And next class we may likely solve an IMO problem in inequality. Depends on a lot of factors. So, but this class is more of laying foundations. What I'm doing on this slide is basically statistics. Okay, statistics that we find in the mathematics Olympiad. Okay, so let's move on. So this is arithmetic mean. It also gives us 5. Geometric mean, like we saw in the previous slide, it's the product of the elements. So we now take the nth root of that product. Okay, so we have 4 fives. Okay, so we have 5 times 5 times 5. There are 4 of them, so 4 roots. So 5 times 5 times 5 times 7 is 625. The foot root of 625 is 5. Okay, harmonic mean, as we saw, the formula is simply the number of elements divided by the sum of the reciprocals of the elements. All right, so there are 4 fives, so 1 over 5 plus 1 over 5 plus 1 over 5 plus 1 over 5. This is 4 divided by 4 over 5. This is 4 divided by 4 over 5, which is 4 times 4 over 4, which gives us 5. Now, one thing I want you to observe very quickly is that we got the same values, 5, 5, 5, 5. And this is one aspect I want you to take notes very strongly, because we're going to see it strongly in subsequent classes. And what is the idea I want you to get from here? That when the values or the observations you're given are equal in value, the various mean yields values that are equal. All right, we have given observations are all equal in value, and we see that implied that resulted in quadratic mean, arithmetic mean, geometric mean, harmonic mean, all yielding the same value, which is what? 5. Okay, it's very important we note this. You would understand this better as we move along. This is what we call the equality case, as we're going to be seeing in the next class. Now, I want to consider another illustration where we have different values. Okay, here we're given the same values 5, 5, 5. So we have the same scenario, same question. Well, this time we have 2, 4, and 8. Okay, 2, 4, and 8. They are different values. So quadratic mean, we take the square of each value, sum them up. There are 3 of them, so we divide by 3. Then we now find the square root. So we have 2 squared is 4, 4 squared is 16, 8 squared is 64, 4 plus 16 is 20, 20 plus 64 is 84 divided by 3. Okay, 3 divides 84, we have 28. So this square root of 28. Now in Olympiad, you're not allowed to use calculator, so I just observed that square root of 28 is greater than 5. All right, so it's sufficient to leave my answer for the purpose of this class. However, we know we can simplify this further. If we simplify this further, it gives you 2 root 7. Okay, 2 root 7. But for what I want to show, it's sufficient. I leave it in this form. All right, so we now move to arithmetic mean of 2, 4, and 8. Okay, sum of the element divided by the number of the elements. So we have 2 plus 4 plus 8 divided by 3. 2 plus 4 is 6. 6 plus 8 is 14. 14 divided by 3. That gives you 4 and 2 over 3. Okay, 4 and 2 over 3. Okay, that's arithmetic mean. Geometric mean is the product of the elements. Then you now take the cube root because you have 3 elements in this case. So we have 2 times 4, 8, 8 times 8, 64. So cube root of 64, which is 4. Okay, harmonic mean, of course, number of elements divided by the sum of the reciprocals of the elements. So we have 1 over 2 plus 1 over 4 plus 1 over 8. We sum them up, you have 7 over 8. So this is 3 divided by 7 over 8, which is 3 times 8 over 7. And this simplifies. This is 3 times 8 is 24. 24 over 7 gives you 3 and 3 over 7. Okay, so we've actually shown, okay, how to compute this mean, but it's not just showing it. There's something I want you to note. Now you see clearly that arithmetic mean, okay, is greater than, sorry, our quadratic mean is greater than arithmetic mean. Okay, quadratic mean is square root of 28, which is 5 point something, because square root of 25 is 5. It's 5 point something, and that's clearly greater than, of course, 4 and 2 over 3. And we see that arithmetic mean is greater than arithmetic mean is greater than a geometric mean. Okay, arithmetic mean is greater than geometric mean. 4, 2 over 3 is greater than 4. We see our geometric mean is greater than our harmonic mean, which is 3 and 3 over 7. Okay, now please listen, because I'm going to be saying some very important things here. They sound obvious and simple, but they're very helpful in solving problems. Now, we are given 2, 4, and 8. The greatest value we have here is 8. And we see that 8 is greater than the quadratic mean. All right, 8 is greater than the quadratic mean. Now, the smallest value we have here is 2, and we see that harmonic mean is greater than 2. Okay, so this goes alongside to re-emphasize what I said in earlier on, that mean always lie between the greatest value and the smallest value. It goes on to re-emphasize that. Now, what I want to take note is that this always works. This always holds. What actually always holds? The quadratic mean is always greater than the arithmetic mean. So arithmetic mean is always greater than the geometric mean. Geometric mean is always greater than the harmonic mean. Always, not just in this example alone. It's always the case. It's always the case. All right. So in maths, we don't just say things like that. We prove them. So I'm going to prove that for 2 values, as I said in the objective. Now, let me say that again. The quadratic mean is greater than or equal to the arithmetic mean. Okay, quadratic mean is greater than the arithmetic mean when we are given different values, just like in this case. But when we are given the same values that we saw in the previous illustration, we see that the quadratic mean is equal to the arithmetic mean. So quadratic mean is always greater than every other, greater than the arithmetic mean, greater than the geometric mean, greater than the harmonic mean. All right, always, as long as the values we are given are different. If the values are the same, quadratic mean equals the rest of the mean, as we saw in the previous illustration. And again, whatever mean you're computing, all right, its value is less than the greatest observation. Its value, whatever mean you're computing, the value you get is greater than the lowest observation. Of course, they are equal to each other if the values given are all equal. Now, we have laid that foundation, which is actually something you should be taught in a statistics class. Now, let's go see what happens, what we actually need to deal with in the world of Olympiad. All right, so this is the first one. Quadratic mean, arithmetic mean inequality. Mind you, this is not a complete proof, right? A complete proof is such that we prove for any number of values, okay? X1, X2, okay? X ellipsis Xn, that is a complete proof, okay? We'll do that hopefully sometime in future, but for now, I want to prove it for just two values. Now, let me inform you that in some countries, this could be an exam question. Okay, one of the questions they bring in the Olympiads. Prove this, given that a and b are positive real numbers, prove that square root of a squared plus b squared divided by 2 is greater or equal to a plus b over 2. This could be an Olympiad examination problem, and of course, what you have following is the solution. But let me explain this in the context of what I've written: AM, QM inequality. Now, when you're given two values a and b, for those of us that have been following, we're given two values a and b. We know that the quadratic mean of a and b is simply the squared. You square each of the values you're given, you divide by a number of observations, and you take the square root, okay? So we're given just two values, so it's a squared plus b squared divided by 2 to square root. So what I'm saying is the left hand side of this inequality is actually the what do we call it? The quadratic mean. All right. The right hand side, clearly sum of the values divided by 2, it's obviously the arithmetic mean. So this quadratic mean, this arithmetic mean. So this is like saying given two real values, positive real numbers, the quadratic mean is at least the arithmetic mean. Of course, at least means greater than or equal to. All right. So all we have here is quadratic mean of two real numbers, positive real numbers, is greater or equal to the arithmetic mean of those same numbers. But we want to prove this. Now, it's important you pay attention to the approach we use in proving inequalities, particularly in the Olympiad examination. So there are basically three procedures you could try out. The first one is that you start with the left-hand side, you work on it, and you keep analyzing it until you now find yourself achieving the value on the right-hand side. Okay, different scenario, you may want to start off with the right hand side to get the left hand side, and there are certain scenarios whereby you'd you would have to carry both sides along and show at some points that they meet. Okay, so basically the approach I'll be using for the rest of the class is that I always start with the ball I have on the left hand side, and I would do some work on it to achieve what I have on the right hand side. Okay, so let's start. So what I have is square root of a squared plus b squared over 2. I want to show that this is at least a plus b over 2. This, I want to show the left hand side is greater or equal to the left hand side is greater or equal to the right hand side. So first thing I do is that I multiply numerator and denominator by 2. So 2 times a squared is 2a squared, 2 times b squared is 2b squared, 2 times 2 is 4. So I now have 2a squared plus 2b squared divided by 4. Okay, now there's a reason why I taught you algebraic identities earlier on. You remember our first set of classes had to do with algebraic identities. It was because you really need them in proving inequalities, improving inequalities. All right, so 2a squared plus 2b squared. Someone asking a question?
Yes, me, Mohammed.
Okay, Mohammed, go ahead.
Yes, so in this kind of questions, can we give, yes, in this kind of questions, can we give values to A and B, like let's A be 2 and B equal to 4?
Yes, you can do that, but that's not how you prove. When you're given A and B to prove for, when you bring in numbers, you're actually proving that it is true for for those numbers you've chosen. So you won't score full marks. In fact, you may never score any mark if you use that approach. So the approach to use is that you stick to the alphabet you're given, or the whatever you're given. You stick to the alphabet you're given, and you work with it to the end. If at any point you bring in numbers, for instance, you could bring in 2 and 3 actually, and of course it works, because in the previous example, that's what I did. I was basically finding the mean. You could bring in numbers and clearly it shows. But what you have not proved that it is true for all positive real numbers. What you've basically done is that you've shown that it is true for the numbers you have chosen. So your proof is not complete. Mathematical proofs are supposed to be complete. So you need to stick with the alphabet, manipulate them, and show that it is true. Mohammed, I don't know if I've answered your question.
Okay.
So at
Yes,
this
sir.
point, okay.
Yeah,
So
please,
Thank you.
okay,
yeah,
Ibrahim, you asking a question?
please, was that this thing
Okay, this,
like
yeah, I've
what
seen it. It's greater than or equal to. Greater than or equal to. That's what it is.
greater than or equal to?
Yeah, it's the same thing. It's at least it's a synonym of it.
Okay.
Just like if I don't know in your school, um, maybe 70 and above is an A. So you said you score an A grade if your score is at least 70. Like if your score is greater or equal to 70. That's what it means.
Thank you.
All right, you're welcome. So we are here 2a squared plus 2b squared divided by 4. So I want to work on the numerator. Now, the idea, it's important that you understand what you want to achieve from the very beginning. All right. What we want to achieve is that we want to make the left hand, we want to show clearly that the left hand side is at least the right hand side. All right. So you must have a plan. Now, this is for many of us, this is your first class um, on inequality. So you may not really know how to start off, but after my next 2, 3 classes on equality, you will know exactly how to start off. All right, because I would in subsequent classes show you the approach. For this class, just follow what I'm showing you and ask questions where you do not understand. So we're here 2a squared plus 2b squared. Now, if you expand a plus b all squared plus a minus b all squared, you would have 2a squared plus 2b squared. And the reason is this: a plus b all squared. For those of us that remember, it is a squared plus 2ab plus b squared. All right. A minus b all squared is a squared minus 2ab plus b squared. So we see that the 2ab in this first bracket would subtract the negative 2ab in the second bracket. So the point I'm making is that a plus b all squared plus a minus b all squared simplifies to give us 2a squared plus 2b squared. Therefore, 2a squared plus 2b squared is the same, is equivalent to, is the same as a plus b all squared plus a minus b all squared. Okay, that's the first point to make. So basically, what we have, this square root is the same as this square root. Now, this is where we want to think through and result comes out. Now, we know that given a fraction, if you reduce the value of the numerator, the fraction becomes smaller. Of course, it's not difficult to see. 3 over 4 is greater than 2 over 4. All right? 3 over 4 is greater than 2 over 4 because the numerator has been reduced in the value. Now, we've already established that a perfect square is at least 0. So we know that a plus b all squared is at least 0. A minus b all squared is at least 0. All right. So none of this bracket gives us a negative value. So if we delete a minus b all squared from this expression, what we are having is smaller. Okay. What we're having is smaller. That means this expression is greater than the expression where a minus b all squared is deleted. I'm trying to explain the link between this expression and the next one. So you observe that in the next expression, the difference is that a minus b all squared has been deleted, has been collapsed. All right, it's not there. So we have that this new expression is less than the previous one. So we have square root of a plus b all squared plus a minus b all squared divided by 4 is greater than a plus b is greater than a plus b all squared divided by 4. And the reason is simple because the numerator has reduced in value. All right, this is a positive. It has why we show a reducing value is because it's like saying we subtracted a positive value out of it. A minus b all squared is not negative. Okay, now greater than or equal to, of course, we have seen that if a minus b all squared is 0, we see that they are the same value. All right, so it's not that is a strict inequality scenario. It's not strictly greater than. It could be equal to. When will equality hold? Equality is this expression is equal to this expression if a minus b is 0. All right, because if a minus b is 0, they are basically the same thing. What you removed had a 0 value. And that's why we say greater than or equal to. Now, what we now basically do here is to simplify. Square root of a plus b all squared, the square cancels the square, so we have a plus b. Square root of 4 is 2. All right, so you see, we started on what we had on the left hand side, and we manipulated it, I think that's the word, and we got what we have on the left-hand side. So clearly, quadratic mean, given two positive real values, what this proof is basically saying is that the quadratic mean is greater than or equal to the arithmetic mean of those two values. And QED, and that's the end of our proof. Okay, let's move on to the next one. So the same approach, I will be working starting with the left-hand side, and I'll work to get the right-hand side. So given A and B are positive real numbers, this basically the arithmetic mean of A and B is greater than or equal to the geometric mean of A and B. Okay, so of course we've established the formulas. This should not be confusing. A plus B divided by 2 square root of A times B. So again, I start with the left-hand side, A plus B divided by 2. Now, the whole, we don't just, in the proof, when you're proving things like this, you must know where you're going to. So we're not just doing anything. Um, your ability to move from the left-hand side to the right-hand side depends on how knowledgeable you are about algebraic identities. All right, so I would advise you go back to those classes we had on algebraic identities, because it's your knowledge of that that helps greatly in this proof. All right, your knowledge of algebraic identities. Okay, now we have A plus B divided by 2. Now the idea here is that I need to work on this A plus B divided by 2 so that I have root AB come out some. So quickly, of course, this is an algebraic identity. What's this saying? Root A minus root B all squared plus 2 root AB gives us A plus B. This is an algebraic identity. You may have to try it out. I think when you expand these things over time, I think on your own, you begin to understand why we do what we are doing. All right, why we do what we are doing. So if you expand root A minus root B all squared, if you expand this and you then add plus 2AB to it, you're going to have A plus B. So basically what that is saying is that A plus B is the same as root A minus root B all squared plus 2 root AB. It's the same thing. Okay, it's the same thing. Now, what we have here is that don't forget that A and B are positive real numbers. All right, so that means their product is a positive real number. The square root of their product is a positive real number. Of course, 2 multiplied 2 is a positive real number. Now we have root A and root B all squared again. This is a positive real number. At least it's not a negative. It's non-negative. That's the appropriate word. Non-negative. Non-negative real numbers are numbers that could be 0 or positive real numbers. All right, real numbers are basically in 3. You have negative real numbers, 0, and positive real numbers. All right. So when you want to consider 0 and negative real numbers, you say non-positive real numbers. If you want to consider 0 and positive real numbers, you say non-negative real numbers. Okay, so what we have here is a non-negative real number. So we see that when you delete or collapse this, the resulting fraction is less than the previous one. Now this expression is greater than what we have when we delete root A minus root B all squared. Again, it could be equal to it. When is it equal to it? When root A minus root B is 0. All right, so that's what we have greater than or equal to. So what I want you to understand here is that by deleting a non-negative real number, the fraction becomes smaller. All right, so this is smaller than this. Of course, I believe you're very familiar with the inequality sign. We could read this in two ways. We could say this 2 root AB divided by 2 less than or equal to this. Or we could say this is greater or equal to this, depending from the direction you're reading it from. I think that should be grade 7, grade 8 work. And we should have done that. So basically, this is greater or equal to this. So we see that we're left with 2 root AB over 2. 2 takes out 2. We're left with root AB. All right. So basically, what we've just shown that the left-hand side is greater than or equal to the right-hand side. Okay. Now, one thing I need to emphasize is that when you're simplifying, you use an equality sign. When you are doing some transformation, like deleting or collapsing something, that's when the inequality sign comes in. It doesn't come in randomly. It comes in when you've actually done something to warrant it bringing it. So simplify like this is equal to this because the equivalent. All right. Now this equal to this. Of course, we just basically simplified. We only brought in the equality sign here when we brought in the argument of we deleted this. So the resulting expression is less than the previous one. Okay. All right. Almost out of time. I think I have this is the last one, and this is the one that looks most interesting. Now, given that A and B are positive real numbers, 1 is square root of AB is greater or equal to 1. Of course, this is the geometric mean of A and B, while the right hand side is the harmonic mean of A and B. Okay, so how do we go about it? Again, you don't really understand why, but what I expect you to understand in this class is what I expect from you is that you follow the arguments I used. Why we do what we do may not really comprehend in the first class, but in subsequent class you get to comprehend the why. So just follow the how, what we are doing. So we have root AB is the same thing as, of course, square root of AB is the same thing as square root of AB divided by 1. So like multiply 2 to numerator and denominator. So we have 2 root AB divided by 2 times 1 is 2. All right, so this is the same thing as this. Now again, what we did next was that we multiplied the numerator and denominator by root AB. Okay, so what we have is root AB times root AB is root AB all squared, which simplifies to give us what? AB. Okay, so basically I'm saying 2 root AB times root AB gives us 2AB. All right, I hope you see that. Now 2 times root AB is 2 root AB. Now again, what we've been doing so far is that we've been dealing with the fraction, and we said when you reduce the numerator of a fraction, all right, when you reduce the numerator of a fraction, the fraction becomes smaller. All right, we know that, right? This is it's simple. Now the opposite is the case with denominators. All right, when you increase the denominator of a fraction, the fraction becomes smaller. Now, it's a direct proportion for numerators, but an inverse proportion for denominators. Okay, all right, okay. So what we've done so far is not done so far. You actually know that when the numerator of a fraction is reduced, the fraction becomes smaller. However, when the denominator of a fraction is increased, the fraction becomes smaller. Now, what did I do here? Now I added a non-negative value to the denominator. Okay, 2 root AB minus root AB all squared. Of course, because it's squared, it's a perfect square. And we see that perfect squares are non-negative real numbers. So I've added a non-negative real number to the denominator. So therefore, the new fraction is smaller. It's smaller than the previous one. So that's basically what I did. Okay, that's basically what I did. Of course, greater or equal to equality case, it's the same thing if root A minus root B is 0. So if root A minus root B gives us 0, that means our new fraction has the same value as the previous one. But we're not certain of it. Okay, so we say greater than or equal to. It's either is greater than or is equal to, depending on what root A minus root B is. So what I now do now is to simplify. So root A minus root B all squared plus 2AB, you simplify that, you have A plus B. So this is 2AB over A plus B, dividing through by AB. So I have 2AB divided by AB is 2. A divided by AB is AB. And I have this as well, and I simplify, and I have this, which is what the question says. So that's the end of the class. I believe you've followed. So I believe you've learned one or two things. In the next week, we'll still continue with inequalities, and we would go deeper than what we've done today. So see you next week.